In terms of architecture, Helm has two sides. There's the client side, which is the Helm command line tool, and there's also the server side, which is called Tiller. The Helm command line tool is what you execute and run in your local command line environment. It uses a templating engine to generate Kubernetes YAML from some source templates that you set up in Helm. And once that YAML has been generated, it then sends those requests to the Tiller that's running on your Kubernetes cluster. Tiller then executes updates inside your Kubernetes cluster to make sure it's up to date with what you needed based on your chart. And the Tiller will make sure that gets released and will add that to the Helm history so that you can roll back to it in the future. To deploy your applications using Helm, you need to package your applications into a chart, but don't worry because a chart is simply a directory with some files in a specific structure. The top level directory name is the name of your chart, so it might be my application or my web service. Below that you have chart.yaml, which stores metadata and version information for your chart. There is values.yaml to store default configuration values that get interpolated into your templates. Requirements.yaml lets you specify dependencies like MongoDB or Postgres. There's the chart subdirectory where your dependencies packages are stored. And finally, the most important directory is the templates directory, which is where we store our source templates that are fed into the Helm templating engine. Inside the templates directory are a bunch of files that look almost like Kubernetes YAML templates, except they also have variable interpolation and the ability to call functions from within those templates. Now, where do we get the values for those variables? We get those from values.yaml, and those functions are declared in helpers. When we run the Helm command line tool, all the files from the templates directory are fed into the engine, where values from values.yaml and the functions defined in helpers are called and interpolated. That templating engine generates Kubernetes YAML that is sent off to Tiller to be applied in your cluster. Once the YAML reaches the Tiller server, Helm creates a new release, which is a runtime instance of your chart. After that, Helm will create the services, deployments, pods, and other resources that are needed to fulfill that chart. Now let's look at a standard example where we might have a Node.js web application, a web server, and a MongoDB database. The web application writes and reads from the database to handle web requests. What we want to do is package the web application and the database into the same chart so that when we deploy one of them, we deploy both of them. And in that way, we can manage them both at the same time. Now, this is an actual Node.js web application that I've got deployed at emojibulletlist.com. You put in a bullet pointed list, it'll look at that list and then it'll extract any emoji. So you can swap the boring bullet points for fancy emoji for pasting into your presentations and your documents. Switching into our code editor, we have a pretty standard Node.js web server where we connect to a MongoDB database. The only important thing to notice here is that we use the Mongo URL to get the URL of the database that we want to try and connect to. And at the bottom of the file, we see we are handling requests and we are sending files when people make requests. And we're listening on port 3003. We've built a Docker image for this application in our Docker file. It's based on the Node.js image. It installs dependencies, it packages everything up, and then it runs the application at the end. If we weren't using Helm here, what we'd have to do is create a Kubernetes service and deployment for our Node.js application. And then we'd have to do the same thing for the MongoDB database. But really, it doesn't make sense for the database to exist without this application. And so what we want to do is to package those two things together so that they get released at the same time, they get rolled back at the same time, and they can get updated at the same time. If we didn't do this, we'd have to do about 10 kubectl commands every time we wanted to change a simple thing in our application. Whereas with Helm, it just becomes a single command that we can easily repeat and easily roll back. To get started, we bootstrap our Helm chart with the Helm create command, passing in the chart's name. What this has done is created a subdirectory there, and inside that directory we have our Helm chart with a layout that looks a lot like the format we saw before. It's created a charts directory, a templates directory, a chart.yaml, and a values.yaml. Now by default, there's a lot of junk in the templates directory, so we can delete all of that except for the helpers template file. In the chart.yaml file, we see some metadata for our chart, so a description, a version, and a name for the chart. Now the values.yaml file contains a whole bunch of basic configuration values that we can just delete because we're going to define our own here. We've cleaned up the bootstrap files, and now we can get started on creating our real Helm chart. To start, we'll declare our dependency on MongoDB by creating a requirements.yaml file. You specify a list of dependencies, giving it the name of the dependency. You specify the repository where we can find this dependency. Here we're putting in the default stable repository. And you also need to specify the version of the dependency. And this is working just like any other dependency manager that you might have used, like NPM or like Ruby gems. Now, how did we figure out this version number? We do a Helm search for the chart we're looking for, and you can see that the latest version was 5.3.4. Let's save that requirements file, then change into our chart directory, and then list out our dependencies using Helm dependency list. Notice that we have one missing dependency, which is the MongoDB dependency we just added. Run Helm dependency update to install this dependency. It'll install it into the current directory so that it gets added to the charts subdirectory. So we go have a look at that charts directory and we see that a chart that's been installed is really just a gzipped archive. We've linked in our dependency, so now let's create a template for our application. We create the application.yaml file, and this is going to declare a deployment and a service that will run our emoji bullet list application. This is going to specify a deployment, which will create a set of pods to run our application, and a service, which will allow network access to those pods. We'll start with the deployment with the API version extensions /v1 beta 1. Now deployment is moving into v1 soon, so you might need to update this. We'll set up a name for our deployment and just call it EBL deployment. And now we set the specification for our deployment. We'll have one pod to run our application. We'll include any pod in this deployment that has the label app set to EBL. In the deployment itself, we're going to create pods that look like this. Our pods will have metadata, so the label app will be set to EBL. And these pods are going to have one container that runs the emoji bullet list image. And as we saw before, we need to pass in the Mongo URL environment variable so that the application can see which database it needs to point to. The name for our environment variable is going to be Mongo URL, and its value is going to look something like this: MongoDB / whatever host the service is running on. Now keep in mind, we don't know this before we generate the Helm chart. .default.service.cluster.local, which is how you reference a service in Kubernetes using a domain name. MongoDB listens on port 27017, and we're going to access the database specified by this variable that we're going to interpolate using our values.yaml file. The next step is to declare our service. This will give us network access to the pods that are created as part of this deployment. The API version is v1. With metadata, we'll set the name to EBL service. With this service, we want it to be allocated a port on the node so that we can access it from outside of the cluster. And we'll use a label selector where any pod with the label app set to EBL will get network requests through this port. We'll set the cluster internal port to 8080. But this doesn't really matter because we don't access it from anywhere, and the target port, i.e. the port that the container is listening on, was port 3003. We make a request from outside the cluster to the node on the port that gets allocated to this service. Kubernetes will route that request through to port 3003 on our container. Looking at this, it looks like Helm chart templates are pretty much exactly the same as Kubernetes YAML. Like, we could basically deploy this on our cluster and it would create a deployment and a service. The problem we hit, however, with Helm is that you want to be able to release the same chart over and over and over again without it conflicting with previous installations of that chart. Where we hit a problem here is that our deployment and our service have fixed constant names, where really we want those names to be unique to each release. The way we solve this is to use one of the helpers so that a name that is unique for each release gets included in our deployment and our service names, as well as the names of any labels that we're going to use. Let's take a look at the helpers template file, which has the eblchart.fullname function that we can call. When this is called, it gets the release's name and any overrides and formats them properly so that we can include them in our Kubernetes resources. We're going to use that full name helper to make each Helm release unique. To do that, we need to substitute the EBL values for the full name values that we saw in that helper. We call that function using Helm's templating language, which is just like mustache or handlebars if you've used any of those. We need to do that everywhere we reference EBL, so we'll copy and paste that into each slot. We need to do that in the service's name, in the deployment label selector. If we left the labels as fixed values that didn't change with each release, then all the releases of this chart would get grouped together. Like, all the pods that have been created would have the same labels and we wouldn't be able to differentiate between one release and the next. And this would just create a mess of conflicts between our pods and our services and our deployments, and we wouldn't be able to keep track of any versions at all. We update those labels in the pod spec and also down in the service. That solved our issue of the conflicting resource names. The other thing we wanted to do was to fill in proper values for our Mongo URL variable. So we need to fill in the host and the DB name based on values that we're going to get from Helm helpers and from Helm values. Our database name is going to be provided through our values.yaml file, so we're going to replace that with a variable interpolation with the .values.db name variable name. For the host value, we're going to call a helper function that will insert the MongoDB database service in here so that we can access it in our application. We need to go and create this helper in the helpers template file, but we'll call it here and we'll call it mongodb.fullname. In the values.yaml file, we'll use that db name variable we referenced earlier, and we'll call the db emoji bullet. That variable is going to be inserted in when the Helm templating engine runs, and now we'll go and create the mongodb.fullname helper function. At the bottom of the helpers template file, we'll add a new helper function. We'll add a new helper called mongodb.fullname. In this function, we're going to return the release name dash MongoDB. One thing to note is that there is a little bit of magic here because the MongoDB chart will call our MongoDB.fullName helper to set up the MongoDB services name. To find that out, you have to go and look at the docs for the MongoDB chart. Back in our application, we can see that we've missed a dot in our template call, so we'll just add that in. A useful trick is to run helm template dot. What that's going to do is run the templating engine without actually deploying those resources on your Kubernetes cluster, so you can see what the templating engine would have generated in a way that makes it easier to debug. You can scroll up on that output and look at the deployment and service that got generated. They would have created a service using the release name. It would have substituted in our MongoDB helper and the database name value that we set up. After that, we can run helm install dot, which will package up our Helm chart and install it onto our Kubernetes cluster. This has gone and created a release in that cluster using Tiller. The release is called Invisible Terrier. It's created secrets, persistent volume claims, pods, services, and deployments, everything we needed to deploy our application. Helm has gone and created these 5 or 6 things on our behalf without us having to run the corresponding kubectl commands. This is a huge win because if we didn't use Helm, we would have to manage all of these independently and keep track of them and write our own documentation about how to update them. And they would all get out of sync and it would be impossible to keep track of once we had tens or hundreds of applications running. We can take a look at the specific pods that Helm has created for us. It's created a MongoDB pod using the chart that we included as a dependency, and take a look at the services and we can see that we've created a MongoDB service that we can reference from our application pods. And it's also created the service that we set up in the application.yaml template, which is our node port service running the emoji bullet list application. Helm has gone and set up our whole application stack with us just running one simple command and writing stuff that looks essentially like our normal YAML and a file that includes some dependencies. If we have a look at the services running in Minikube, we can see our application services there. We'll run Minikube service with that service name, and that will open it up in our web browser. We can see in the browser that it's spun up our whole application stack and it's ready to go. We haven't had to install Node.js or install MongoDB and get those things to point at each other. It was a